Okay, so now we're going to see how the relaxed version of the period finding problem that we talked about in the last segment suffices to actually factorize integers. Okay, and this actually remains the premier example of a potential quantum speedup. Okay, I say potential because of course we don't have any classical lower bounds on the complexity of factoring, but after years and years of people trying, the best known classical algorithms for factoring are run in sub-exponential time. Okay, so the best rigorous bound on the complexity of a classical algorithm for factoring runs in time exponential in the square root of log m, where m is the number that you want to factor. Okay, and based on some number theoretic assumptions, there's algorithms that have complexity exponential in the cube root of log m. Okay, and what Shor can give is an algorithm whose complexity is only polynomial in log m. Okay, so here I'm using this O tilde notation. So basically what that means is that's just hiding lower order factors, so factors that are polynomial in log m. Okay, so yeah, so just so you know what that means. Okay, so we've already seen the whole, the entire quantum part of Shor's algorithm. So this lecture is going to be just completely classical reduction from order finding to actually finding a non-trivial factor of an integer. Okay, so one definition that we need is the multiplicative group of integers modulo m. So this is just a set of integers which are relatively prime to m and are between 0 and m minus 1. So it's that set under the operation of multiplication modulo m. Okay, and I'm going to denote this group as like this. So, and I'm going to read this as zm times. Okay. Okay, so if you take an element in this group, its order is the least positive integer s, such that x, if you take an element x in this group, its order is the least positive integer s, such that x to the power s is equal to 1 mod m. Okay, so that's the order of an element of this group. And let's just look at an example here. So if m is 21 and we take x equals 2, so 2 is relatively prime to 21. And let's just look at the powers of x modulo 21. So we have 2, we have 4, we have 8, we have 16, then 16 times 2 is 32. So mod 21, that's 11. 11 times 2 is 22. Mod 21, that's 1. Okay, so now we found the order of 2 mod 21. So that's, which is 6, right? So 2 to the power 6 is 1 mod 21. So this is actually the function that we're going to want to find the period of using Shor's algorithm that we talked about in the last segment. So it's this function here. So f of a is equal to x to the a, x to the power a mod m. Okay, so you can just view this as a function on the integers, right? A can be any integer, and you can look at the power of x to the power a. But for this application to Shor's algorithm, we're just going to look at a finite truncation of this function. Okay, so we're just going to consider it as a function from m squared to m. Okay, and that's basically just we want to see enough periods so that Shor's algorithm is able to figure out the period. And last time we saw that Shor's algorithm could work as long as you took the size of the domain to be something like the square of the size of the range. Okay, so let's just check that this satisfies the conditions of this more relaxed version of the period finding problem that we saw last time. So let's start with number 3, because that's easy. That's by design, where we can choose the size of the domain to be m squared, so that we see at least m many periods as we needed in our proof in the last lecture. Okay, let's see that it satisfies the injectivity assumption. Okay, so suppose that x to the a1 was equal to x to the a1 plus a2 mod m. Well, that means that x to the a2 must be 1 mod m, okay? Which in turn means that a2 must be at least s, right? Because s is the least positive integer, such that x to the s is 1 mod m. Okay, so a2 must be at least s, so that in particular that means that f of 0 through f of s minus 1 must all be distinct, okay? And finally, the periodicity condition. So x to the a plus s, well, that's equal to x to the a times x to the s, and x to the s by definition is 1 mod m, so that's just equal to x to the a. Okay, so this f also satisfies the periodicity condition. Okay, good. So another interesting thing now about this integer factoring problem is that up to now, I think all of the quantum algorithms that we've seen have been in the query model. Okay, so we just, we assume that someone gives us this unitary that computes a function f. Okay, so this is the first time that we're actually leaving the query model. And now we're going to, compute the function f ourselves. Okay, and this f, so this, modular exponentiation mod m, luckily we can compute this function efficiently, even classically, okay? So how can you do that? Well, you can use this, what's called the square and multiply method. So basically, if you compute, x squared, x to the 4th, x to the 8th, etc., mod m, all the powers of 2, then, by computing those, then, multiplying the appropriate powers of 2 together, you can compute x to the a mod m for any value of a, okay? And if you work out the complexity of this, it's something like O tilde of log m squared many classical operations needed to compute f of a, okay? So here I've written out the low order terms, but we don't really care too much about that. Just think about this as, it's roughly log m squared many operations. Okay, so we actually have a classical circuit of that size that can implement f for us. And we can make that a classical reversible circuit and then just use that in our quantum algorithm. So this actually turns out to be the bottleneck of Shor's algorithm, okay, actually computing this function f that dominates the complexity. Okay, good. So so now we can use the quantum part of Shor's algorithm, what we saw in the last segment, to actually compute the period of f. So to compute the order of some number x. So now let's see how, if you can do order finding, then you can actually find a non-trivial factor of m, of this integer m, okay? So the key idea to that is to find a number x such that x squared is equal to 1 mod m, and x is not equal to 1 mod m or not equal to -1 mod m. Okay, so let's suppose that you can do that. You find such an x. Well, this equation, x squared equals 1 mod m, that says that x squared minus 1 is equal to 0 mod m. So you can factorize x squared minus 1 into x plus 1 times x minus 1. And neither of these is 0 mod m, right? Because x is not equal to plus 1 or minus 1 mod m. So we have x plus 1 times x minus 1 is equal to 0 mod m. And neither one of these two factors is a multiple of m. So what that means is that x plus 1 must share some non-trivial factor with m. And x minus 1 must also share some non-trivial factor of m, right? Because m doesn't divide either of these alone, but it divides their product, okay? So all the factors of f, are coming from by combining factors of x plus 1 and x minus 1, okay? Okay, so so if we do this, if we find such an x, and we've just said that x plus 1 must share a non-trivial factor of m, must have a non-trivial factor of m. So if we just look at the greatest common divisor of x plus 1 and m, this is going to give us a non-trivial factor of m, okay? And again, this is something we can do classically efficiently. Okay, so let's see this with our example where m is 21. So if we look at 8 squared, so 8 squared is 64, and so mod 21, that's going to be 1. But 8 itself is not equal to plus or minus 1 mod m, okay? So 8 is an example of what we're looking for. It's a non-trivial square root of 1 mod m, okay? So yeah, so can you think of another one? I know you're watching at home now, but just take a minute to think about that. Okay, so another one, since this is a property of the square, would be minus 8, right? If we look at minus 8 squared, minus 8 squared is also 64, right? So that would also be equal to 1 of mod 21, right? So minus 8 mod m, that's like 13, right? So 169 is also equal to 1 mod 21. Okay, so yeah, so these non-trivial square roots are going to come in pairs. Okay, so if we find this non-trivial square root, and then we, just to look at our example, so then 8 plus 1 times 8 minus 1, so 9 times 7 is 63. So yes, indeed, that is 0 mod 21. And 9 shares a common factor of 21, 3, and 7 shares a common factor of 21, just 7. Okay, so so you see how doing this lets us find a non-trivial factor of in this case 21. Okay, good. So how are we going to find a non-trivial square root? Well, we're going to use order finding, okay? So let's think about how we might find a non-trivial square root using order finding. So let's look at our example again. So where we computed the order of 2 mod 21, and we saw that that was 6. So 2 to the 6 is equal to 1 mod m. But in this case, the order is actually even, right? So that means that 2 cubed squared is going to be equal to 1 mod m. So we've actually found a square root of 1 mod m, right? So there's just 8, what we just talked about before. Okay, so in general, if we find an element whose order is even, then we've found a square root of 1 mod m. Okay. Okay, so the other condition that we needed, right? We needed not just to find a square root of 1 mod m, but we need this other condition that that the square root is not equal to plus or minus 1 mod m. Okay, so not equal to 1 mod m, that's easy because if we find something whose order is greater than 1, then it's not going to be equal to 1 mod m. No, I'm sorry. So right, so in this example, we know that the order of 2 is 6, right? So that means that its square root 2 cubed is not going to be equal to 1 mod 21 because its order is 6, right? So to the power 3, it can't be equal to 1. Okay, that's going to hold true in general in this kind of framework, right? If we find a number x such that x to the 2k, whose order is 2k, so x to the 2k equals 1 mod m, then looking at just x to the k, that can't be equal to 1 mod m by the definition of order. Okay, now for the other case, we kind of just have to get lucky. Okay, so in this case, we are lucky that 8 is not equal to 1, not equal to minus 1 mod 21. So we can't kind of guarantee that a priori. We just have to kind of get lucky, but you can actually prove that you get lucky fairly often when you follow this approach. Okay, so in particular, the lemma is the following. So if m is odd and it has a prime factorization that looks like this, so really the important thing from this equation is the number of prime factors. So in this case, it's k. Then if you pick an x, I'm sorry, this should be times, not asterisk. This is ZM times. So this multiplicative group of mod m. So if you pick an x in this group uniformly at random, then with probability at least 1 minus 1 over 2 to the power k minus 1, the two conditions that we want will hold. Okay, so the order of x will be even, and x to the s over 2 will not be plus or minus 1 mod m. Okay, so you see if k equals 1, then this basically gives nothing, right? This is like 0. Okay, so k equals 1, that means that m is a prime power. So we're going to have to handle that case separately, but there are efficient classical algorithms to check if m is a prime power. Okay, so that's not a hard case. But you see that as long as k is at least 2, so m has at least 2 distinct factors, then this probability is going to be at least a half. Okay, so with the probability at least a half, when we choose an x uniformly at random, we're going to get lucky. And the two conditions that we need are going to hold. Okay, good. So that gives us our whole algorithm. So first we just check if m is even or a prime power. So that can be done quickly, classically. Then we just choose a random number between 0 and m. And we compute the greatest common divisor of x and m. So if this is not 1, then we've already found a non-trivial factor of m, and we're done. If this is 1, then x is in the multiplicative group mod m, and we can compute its order. Okay, so now we compute the order s of x, using the period finding algorithm. And the last lemma said that with probability at least a half, we are in the good case where the order will be even and x to the s over 2 will not be equal to plus or minus 1 mod m. And in that case, we've found a non-trivial square root of 1 from which we can get a factor. Okay, so this holds its probability half. So we're just going to need to repeat steps 2 and 3 a constant number of times in order to get success probability, whatever constant you want, say 3/4 or something. Okay, so we just need to repeat steps 2 and 3 a constant number of times. Okay, so what's the complexity? So the main complexity comes in step 3, that is computing the order of x. So to do that, we have to do this relaxed version of the period finding problem. So we said that we had to repeat the quantum procedure like log n many times to to get to correctly compute the order with high probability. So that's a factor of log n. And then each time we run the procedure, well, we have to do the Fourier transform twice. So we know that's like log m squared many gates. And now we also have to compute the function f. And that is also like log m squared times some lower order factors time. Okay, so overall we get something like log m squared times terms that are log m and smaller. Okay, so overall the running time is O tilde of log m squared, and that's what we wanted to show.